Welcome to another lecture, in particular the fifth lecture in week 3 of Machine Learning Foundations. We're going to continue the discussion on linear algebra side of things. And the topic we are discussing is least squares and projections. So far we have understood that you can solve least squares problems either directly by taking derivatives or more simply by solving a system of equations using projections. And we'll try to understand this by example in this lecture, where we'll look at a very simple one-dimensional example which can be seen as curve fitting. You're given a bunch of data points. You want to fit the best line. We'll understand this by solving the least squares problems using the projected system of equations. Yeah, so we'll look at ordinary least squares. The simple case. Simple case, you have the simple case in one dimension. So imagine you have data, imagine you have a data set, say x1 b1 x m bm. Now want to find a least squares fit, which is like I want to fit such that beta equals theta xi plus some theta prime. This is the constant offset. Yeah, this is the offset. Yeah, so this is a linear fit. Now you want to find such a fit for I equals 1 to m, all the data points. So what you do is, this system of equations so let me call this one system of equations is equivalent to, just put it in a matrix form. What you do is put x1 until xm, add once 1 times theta theta prime, not theta prime, theta double prime equals now this is like a theta equals b, where theta equals theta prime and theta double prime. Your job is to find, a theta equals b again may not be solvable. The same story that we have seen before. A theta equals b may be inconsistent. So the least squares approach is to minimize this error b minus a theta square which is the same as b minus theta prime x1 minus theta double prime square plus dot 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 b1 minus plus again until bm minus theta prime xm minus theta double prime square. Suppose let's call this theta hat prime, theta hat double prime. It's the arg min over theta tilde theta arg min over theta p minus a theta square. So pictorially what you are doing is, imagine you have points like this. Okay, let me draw the line. So let's say this is x1 comma b1, x2 comma b2, x3 comma b3, x4 comma b4. Let's call this p1, p2, p3 and p4. You want to find these points p1, p2, p3, p4, and these distances are the errors E1, E2, E3, E4. We want to find the line that minimizes the sum of the square distance. If the points B1, B2, B3, B4 already lie on a line, then the projections would be the same as the original points. And the square error would be 0 and Ax equals b can be solved. Now, if not, then minimize the square error. Okay, I made a mistake. I should have used theta. So, look at a quick example to make this idea clear. Imagine, let's take a very simple example. Imagine you have the following A theta equals b, where A is just 1, 2, add the constant offset. You have theta prime, theta double prime equals 1, 1, 3. So, this is your A theta equals b. The first thing to check is this system solvable? Is A theta equals b consistent? Now, how do you do this? You just do Gaussian elimination. So, just throw in minus 1, 1, 2, 1, 1, 1 and then 1, 1, 3, or does B belongs to column space of A. Now, this, if you do Gaussian elimination, I am not explaining each step, but I hope it's obvious. Gaussian elimination was covered in an earlier course, and it's a fairly basic algorithm for inversion and checking if system of equations is solvable, all that. So, I am just reducing it to the echelon form 0, 2, 2, 0, 3, 5, and this becomes 1 minus 1 minus 1, 0, 1, 1, 0, 3, 5, and that becomes 1 minus 1 minus 1, 0, 1, 1, and unfortunately 0, 2, 0, 0, 2. So, this just implies inconsistent A theta equals b, or b does not belong to column space of A. So, we can go ahead. So, the point is, the first thing to check is, given a system, is it even consistent? If it is already consistent, there is no point going and solving an alternate equation when the original set of equations is already solvable. Now, in this particular case, unfortunately, the data it says that it has you have an inconsistent system. So, we will do least squares. So, for least squares, what you need to do is to solve A transpose A theta hat equals A transpose B, where theta hat is theta hat, oh god, theta hat prime, theta hat double prime. This is what you need to solve. So, what is it? I would encourage you to just pause the video now and work out all of the details of this exam. You are given the recipe, just please work out all the details on your own. Find theta hat prime, theta hat double prime after finding A transpose A and looking at this system of equations. So, I am just going to give out the solution, but I strongly encourage you pause and do this. So, this is 1, 1, 2. 1, 1, 1. This is nothing but 6, 2, 2, 3. And you can also check A transpose B equals 1 into B 1, 1, 3 equals 6, 5. So, what you have is A transpose A theta hat equals A transpose B is the same as 6, 2, 2, 3 theta hat double prime equals 6, 5. This is just a normal, high school simultaneous set of equations which can be solved, which is equal to 6 times theta hat prime plus 2 times theta hat double prime equals 6, 2 times theta hat prime plus 3 times theta hat double prime equals 5. And this leads to theta hat prime, which is okay. The first thing that comes out easily is theta hat double prime, and the other one comes out to be 4/7. So, we got the theta hat vector, which is the least square solution is theta hat equals 4/7, 9/7. So, the best line in the least squares sense through the given data is this line. It is 4/7 times x plus 9/7. This is the best line. Now, recall the data, using this B, whatever we got, the input point. So, just go back to the system of equations that you have here. The input points are -1, 1 and 2, and the output is 1, 1 and 3. And we just figured the best line is this. So, the projections, what are the projections? The projections are, what is P1, which is projecting the very first point. P1, which is projecting the very first point, would be 4/7 into something plus 9/7. The very first point is -1, leads to 5/7. The projection of second point, I am not going to give out the full thing, but it is 13/7, x is 1 there, and this one is 17/7 for x equals 2. Okay. Now, given this, it is clear that these quantities are not on a line, because you would have recorded the original points. Yeah, the original set of points, the original data is not on a line. So, the square error is going to be greater than 0. Let us calculate the square error, which is equal to B minus A theta hat square This is the minimum or the least squares, and this is going to be B is 1, 1 and 3 if you remember, and 8 it had we have just figured out just P1, P2, P3. So, you get 1 minus 4 by 7 plus 9 by 7 this square, and plus 1 minus 4 by 7 plus 9 by 7 square plus 3 minus 8 by 7 plus 9 by 7 square. Sorry, the square is outside. And this whole thing turns out to be minus 2 by 7. Let me calculate the E. Okay, I want to write this as E. E is minus 2 by 7 because I want to find the projection, minus 6 by 7 and 4 by 7. That is your vector E. Now, you can observe. So, the point is if you look at the normal picture here, you have a line, you have minus 1, 1 and 2, and you are looking at some point here, some point here and some point here, and then your projections would be here, projections P1, P2, P3. Okay. Now, you can look at this in terms of some space also, okay, and this is spanned by two vectors. This is a plane that you are looking at, okay, and the vector B is somewhere outside. B is 1, 1, 3, and these two are the two columns. Say this is the very first column, which is minus I think minus 1, 1 and 2, minus 1, 1 and 2, 1, 1, 1, and now E is orthogonal to this. So, we saw that, okay, let me highlight, somewhere here is P, which is equal to, you can calculate this, 5 by 7, 13 by 7, we just calculated this, 17 by 7, and E is, the orthogonal part is whatever we calculated, minus 2 by 7, minus 6 by 7, not minus 2, plus 2 by 7, minus 6 by 7 and 4 by 7 should be a plus. And you can see that E is orthogonal to minus 1, 1, comma 2, and E is also orthogonal to 1, comma 1, comma 1. So, E is in the orthogonal space. Yeah. So, that is what I wanted to show here. Yeah. Do I have a typo here? Yeah, 5 is. Okay, that's just a typo here. This should not be squared. So, I am calculating E and there is no square here. So, the point is, this is where the connection is. E is going to be orthogonal to this space. So, E is going to be somewhere above, and so let me write this. This is going to be E. Yeah, make this clear. And this is P, and E equals B minus P, which is equal to this. Yeah. So, that completes the least squares fit. We will look at some more topics related to this very soon. Please go over this, try to solve some examples. Okay, a quick summary before we end this lecture, and also this week of the week 3 of this course. This The main learning from this lecture is that we looked at an example, say a linear system of equations, say A theta equals B. And the motivation for this linear system of equations was curve fitting. So you're given a bunch of data points and you want to fit the best line through these points that runs through these points. And best is qualified in terms of least square. So you want to fit the line that minimizes the sum of squares. And what we did was we solved this problem using the projected system of equations. And before that, we also saw that these points are not on a line, which is to say that A theta equals B is not solvable. B is not in the column space of A. And so we had to do projections. We had to project these points onto a line. And we solved this explicitly through the example and understood the concept of solving least squares, and also hopefully one got a good grip of projections through this particular example, curve fitting example. Moving on, in the next lecture, what we'll do is we'll generalize this curve fitting example to a multidimensional case. The ideas won't be new, it's the same idea. We'll just write down the system of equations in a more general vector parameter setting, not just projecting onto a line, but projecting onto a general subspace. And that would be characterizing the linear regressions or least squares regression. We'll understand least squares regression, which is the first most simple machine learning method that you can look at, and you can also understand well from a linear algebra viewpoint.